Hi, I'm Paul. We're doing Leetcode must-know interview questions. Today's challenge is binary tree maximum path sum. This is rated as hard. The challenge is a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. Okay, so that makes it harder. The path sum of a path is the sum of the node's values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay. Let's look at an example. The first example is really too simple to be useful. In a way, this is like things that we've done before, with path sums and depth first search, either by creating a stack or doing it recursively, which uses a stack. But now there's a new twist here. For example, this one, the maximum path sum is actually this right here. This 1527. How do we find a path like that? And there's an insight here, well, maybe a couple of insights that should solve the problem. We're still going to do a depth first search recursively. So, if we start at the root, we go to the left, there's just a 9 over there. All right, it's more the right side is more interesting. We go to the 20, and the value of this node is going to be whatever value is in the node plus the max value of the left subtree, which is 15, plus the max value of the right subtree, which is 7. So we put all of those together, we get 42. And we have a variable where we're keeping track of the maximum sum that we've seen. And so we would put 42 in there. It turned out that 42 is the maximum path. But there's a difference in what we pass back up the tree in order to, in order for higher nodes in the tree to calculate this accurately. We can't return 42 from this node because if a node comes down here, it can't get 42 unless it goes to 20, and then it goes to 15, and then it goes back to 20, and then it goes to 7. That's against the rules. So what we return from each node is the value of the node plus the maximum of the right or left subtree. In that case, it's 15. So what we return back up to the calling node is 35. We've got a value of 42. We found that, but we passed 35 back up the tree. The other thing is there may be negative nodes, and we want to ignore those. We want to for example, if this was negative 15. What we don't want to do now is add the left subtree and the right subtree, because we get 20 minus 15 is 5 plus 7 is 12. So this node is worth 12, but it's not worth 12. If we just ignored the negative value, it's 20 plus 7. It's worth 27. So essentially, we're going to zero out any negative nodes. With those constraints in mind, we can try an implementation. think I may need more room here. Let me scoot that. Let me scoot that over. All right, let's try it. So we're going to have a class variable. Let me skip a line. We're going to have a class variable, an integer. We can call it max sum, and we initialize that to the smallest value that we can initialize it to, so that anything we find will be bigger than this value. Integer min value. Okay. Wait a minute, I put that in the wrong place. That is a, I want that to be a class variable. So actually that is up here. Whoops. All right. Private class variable. Okay, public max sum. Eventually we are going to return the max sum, but we're also going to recursively call a routine to do a depth first search. Max path sum, we'll call it calculate max sum, and we will pass in the root node. Okay. Let me copy that. This can be a private method. Private, it's going to return an int, and we're going to calculate the max sum. The input is a tree node. We'll call it node here. We don't call it root because the first call it's going to be the root, but after that it's just going to be a node. If node equals null, return 0. Now, you might say, well, but we were guaranteed that the root wouldn't be null. We are guaranteed that the root will not be null. That's the range of nodes that we could have. We could have one node, or we could have 30,000 nodes, or something in between. But there are other possibilities here. For example, when you get to leaf nodes, we're still going to call calculate max sum on left and right, and they're going to be null, and we want to return 0. I mean, when we get here, we don't know that that's a leaf node. We don't know it's a leaf node until we try to access the left node and the right node. So that's really for handling calls from leaf nodes, and it's possible that a node may only have one leaf node as well. So okay, but if we try to call this and the node is null, we will return 0. All right, int left max sum equals, and this is how we're going to cancel out negative values. I'll explain it a little bit more after I write it. And this is calculate max sum. and we're going to send in node dot left. Okay. So in the example that I postulated earlier, which would be, well, what if this was negative 15? Then calculate max sum for this node is going to return negative 15. But we don't want negative 15. We will take the max of either 0 or whatever that returns. Now, if it returns 15, we'll take the 15. If it returns negative 15, we'll take the 0. We don't want to deal with negative numbers being returned from subtrees. All right. The next thing we want to do is actually very similar to what we just did. Which is get the right max sum by sending in the right node. All right. Once we do that, we check whether the sum of the node plus the left subtree plus the right subtree is greater than any path sum that we've previously seen. So we'll say max sum equals the max of the current value of max sum or node.val plus left max sum plus right max sum. Okay. Now again, that's not what we return. What we return is the node val plus the maximum subtree, because any path coming down into, in our example, 20, even though we have a sum of 42 there, if you come down into that node, you can't get 42. You can only get 35. All right. Node val plus math max. Let's do this. Left max sum, right max sum. Okay. I think that's it. The coding, I mean, it's hard. It's hard to figure out. It's not hard to code. It's just kind of hard to figure out how to make it work with a depth first search. And like I said, the way that we make it work is we do not pass that this node has a max path. Well, this path has a max path sum, but we don't. I'm running it off the page here. We have a max path sum here, but we do not send that back up the tree. We just send the max using one subtree. And the other thing is we ignore negative subtrees. Okay. With that said, let's try and run this and see what happens. Compile error, return max sum. All right. Semicolon. Try it again. Accepted. I'm going to try not to appear surprised. I mean, pleasantly surprised, but okay, let's submit it. What did we get? Okay. And actually we got some good numbers on it, although it sort of seems like everybody got the same everybody got the same number. When you get down to it, there's really not a bunch of different ways to do this. It's a depth first search with a little bit of a twist. Okay, so we got that. We did well on the memory allocation. Actually, the memory allocation spread out a lot more. That may have to do with programming languages. I don't know. All right, that's it. That is, what is it called again? No, not submissions. I want the description. It is called binary tree, maximum, path, sum. We have a few more binary tree. We have a few more binary tree challenges in the list. I know at least some of them do breadth first search, so we'll have a chance to look at that. But yeah, I hope you enjoyed it. Please feel free to subscribe, like, comment, and see you next time.